Hello everyone. So since we are not going to have any recitation session before the final, I decided to record solutions of the suggested problems for the last discussion session. So in this video I'm going to look at the problems from chapter 7, and another video I'm planning to record the solutions for the problems from chapter 38. So these problems you can look them up in Auto class under suggested problems heading. Okay, so the first problem from chapter 37 is problem 55. How much energy is needed to ionize a hydrogen atom in the n equals 3 state? Okay, so this is 55. So in a hydrogen atom we have this diagram of energy levels, usually shown like this. So this corresponds to n equals 1, n equals 2, 3, up to n equals infinity. Right, and then we have this formula for the energy levels. The energy levels correspond to minus 13.6 electron volts z square by n square. Right, so the difference between these energy levels, this thing here, is 13.6 electron volts, the ionization energy for ground state hydrogen atom. Right, so if you solve enough number of problems, you're just going to memorize that number. Now, one thing I want to emphasize here is that this scale is not distance. Right, so the vertical coordinate here is not some distance; it's just some energy scale. So the distance itself would look like R1, 4R1, 9R1, and so on and so forth, 16R1. And so on and so forth, 25R1. So the distance, Rn, would correspond to n square times R1, which we sometimes write as n square A naught. It's R1 or A naught is known as the Bohr radius. It is of order in angstrom, but it just increases, right? As you see, this actually comes to some limiting value. This difference corresponds to some 13.6 electron volts. It doesn't correspond to a distance, right? If I was writing distance here, this will just tend to infinity. It will go to infinity as square of n. Okay, so in this problem, they're asking for how much energy is needed to ionize a hydrogen atom that is in the n equals 3 state. So the ionization takes place. So n equals infinity corresponds to ionization. Right. So if you kick an electron to n equals infinity, then you ionize the atom. The electron is no longer bound to the nucleus. Of course, if you give more energy, then that's what's required for ionization. Then at infinity, your electron is going to have some finite energy. Right. If you just give enough energy to ionize, then at infinity, your electron is going to have zero energy. Right. So that's the idea. Now here, what we need to calculate is the energy required for ionization. So what we need to calculate is E infinity minus E3. So E infinity is 0, right? N goes to infinity, of course, makes this E infinity 0. This is also something you could know. This is our actually choice. We choose E infinity to be 0. And then this E3 has this minus sign that cancels that minus sign. So this is going to be 13.6 electron volts divided by 9. Right, and the numerical value for that is going to be 1.51 electron volts. Right, so if you give this much energy to an electron at n equals 3 level of hydrogen atom, then it's going to it's going to become unbound from the proton. The atom is going to be ionized. The energy of that electron is minus 1.51. So if you make it 0, then it means that the system becomes unbound. By convention, a system with a negative energy we consider to be bound, and a system with a positive or 0 energy we consider to be unbound. Right? So the answer in this case is just 1.51 electron volts. It's a positive quantity. Okay. So the next question is very similar. Calculate the ionization energy of double ionized lithium 2+, which has Z equals 3. Okay. So this is problem 57. Right, I'm going to erase this because it's no longer exactly applicable. It's not 13.6 anymore, but this formula is applicable, so I'm going to keep that. So we have lithium, which has Z equals 3. It has 3 protons in its nucleus, so its atomic number is 3. And we start at n equals 1. And again, we are looking for ionization energy. We are looking for this, minus En. And this is going to be minus mixed plus, and 13.6. Excuse me. Electron volts. Now this time we multiply by 3 square coming from z square term and divide by 1, n equals 1. So instead of dividing by 9, we are now multiplying by 9, and the answer of this multiplication is 122 electron volts. So for a lithium plus 2 or 2 plus plus, I don't know, as a single electron. So this formula is applicable to atoms with a single electron, right? So we call those hydrogen-like atoms. So for helium, you need to ionize it once. For lithium, you need to ionize it twice. For something that has like 80 protons, you need to ionize it 79 times. So it's just one electron is going to remain. Then our Bohr model and this formula becomes applicable. Okay? Though perhaps for very high numbers, again, you might run into some difficulties. But in general, we say that this is applicable. All right, so yeah, this is 122 electron volts. Now let's take a look at the next question. 65. Determine the electrostatic potential energy and the kinetic energy of an electron in the ground state of hydrogen atom. So this is problem 65. We want to look at the energy, the kinetic energy and the potential energy which arises from electrostatic interaction for the ground state of hydrogen atom. 65. What's the kinetic energy? What's the potential energy? Now, the way I want to solve this is to use a very useful. Sorry. Let me switch to my whiteboard here. So the way I want to solve this is to use a very useful theorem called the virial theorem. So my field of study is celestial mechanics. It's very widely used in that field, but it's also applicable to this problem because, Coulomb interaction is the same as gravitational interaction. And that theorem says that the total energy, or the kinetic energy, is just going to be minus a half the potential energy. Right? And since we know that the potential energy plus kinetic energy is equal to minus 13.6 electron volts, from these two, we can easily calculate that the potential energy is twice this value. So that's 27.2 minus 27.2 electron volts, whereas kinetic energy is just minus this value, 13.6 electron volts. Right? So the solution of this equation, which arises from virial theorem, plus this equation, which we know that this is the binding energy of a electron in the ground state of hydrogen, yields to this result. Now, how do I get this though? How do I obtain this result? Well, the way to obtain that result is to write down the force and kinetic energy and so on and so forth. So let me write this down. So the potential energy for the Coulomb interaction we have is minus 1 over 4 pi epsilon naught q square, where q is just the charge of electron, or the absolute value of the charge of electron if you want, divided by r. Right? This is the potential energy. The kinetic energy is a half mv square. This is a non-relativistic formula, and it's a standard exercise to show that this is actually applicable for the electron in the ground state of hydrogen atom. But we are going to be utilizing this as it is done in the book for this section. And we can write the force. So the force is going to be 1 over 4 pi epsilon naught q square by r square. This is just the Coulomb force, but because our electron is going on a circular orbit around the proton, this must be equal to the centripetal force, right? So m times v square by r. Okay, so I can make some cancellation here. This r square cancels this, and from this we can see that this is the expression for potential energy, right? So if I divide both sides by a half, it follows that kinetic energy is just minus a half potential energy. And so as I said, this is a virial theorem, and this is applications in celestial mechanics. It just, in that case, it just follows from by replacing this q square by m square, you get pretty much the same result. Right? So, and then by combining these two, you get the desired result, the expressions for potential energy and kinetic energy. And there is an alternative solution in the solution manual, but I wanted to show you how you can utilize a virial theorem in this case. Okay. So the next question is problem 70. Suppose an electron was bound to a proton is in the hydrogen atom, but by gravitational force rather than by the electric force. What would be the radius and energy of the first Bohr orbit? Okay. Yeah, let me switch scenes. So this is coming closer to my field, celestial mechanics, but at the same time, this quantization is of course completely irrelevant for celestial mechanics. But we are going to write down the interaction as gravitational interaction. So this is problem 70. Okay. So here for the potential energy, I'm going to have the expression minus g m proton m electron. Instead, actually, I'm going to just say capital M and small m divided by r for the potential energy. So this capital M is mass of the proton and small m is mass of the electron. Okay. So the kinetic energy is going to be a half mv squared, and we are going to have the same situation that g m over r square is going to be m v square by r. So the electron is going on around a circular orbit. There is also, of course, the motion of proton, but for our purposes, we just neglect this. Then this formula actually holds. All right, so we have this cancellation. We get this gm over r is equal to v squared. Right, so we get an expression for v squared. Now, to move further, what we need to do is to put the quantization condition, right? And the quantization condition is written is mvr is n times h over 2 pi, right? Or nh bar. It's sometimes written. It's reduced Planck's constant or Dirac constant, whatever you want to call it. And we are going to look at the ground state, I believe. Let me check if that's what they're asking. Otherwise, I'll keep the n. First Bohr orbit, so it's the ground state. So we have the situation mvr is equal to just h bar. Okay. So this is n equals 1, ground state, first Bohr orbit. All right. So I want to get an expression for for r. What I can do is I can solve this for v and then substitute into one of these expressions and then get an r. So I can write this v in terms of r and then substitute in here, and I'll get an expression which I can solve for r. So let's do that. So this gives me v equals h bar over m times r. Then this v square becomes h bar square by m square times r square, and I get this cancelled. From this, I move this to over here, gm goes down below, r equals h bar square by g capital M small m squared. And so that's one of the things they're asking, radius. And then the energy is going to be the sum of these two, right? And for that, well, we can again show that this is actually minus 1/2 of that. Is there an easy way to show this? Well, you proceed exactly the same way. So what we need to do is to really just calculate. So total energy, E total, is potential energy plus kinetic energy. And by the virial theorem argument I've just shown you, this is actually equal to a half potential energy. Or this is equal to minus the kinetic energy. Right? So you can choose either one. And which one is easier? I think this one is easier. So half potential energy will be easier. This will be a half. For the potential energy we have G m divided by R, but R is this, so this is h bar squared, and then this becomes G square m cube, and I need the negative sign. Okay, that's coming from here. Okay, so this will be the total energy expression. The total energy is going to be negative. Otherwise, what you need to do is to calculate this, and then calculate this by using this expression, and again substitute the R value. So let's show that just very quickly. Let's substitute this expression into here and see that we're actually getting the same thing, same expression as over here. So the kinetic energy is going to be a half m. V square is h bar square by m square r square, so this goes away. This is a half h bar square by m. Now r square is there is a problem somewhere. So when I made this substitution, is there a problem? Let me check. Yeah, I don't know. Let's just proceed. So we'll see. So r m times r square is going to be h bar to the 4 m square. I got lost. So r is what? H bar to the 4 times g square m square m to the 4, and if you simplify we get a half. So this becomes cube, this becomes square, h bar square g square m cube, and it is the same expression. Okay, so you could just do this. You do it this way: make a substitution for the potential energy and kinetic energy, and then add them up, or you could just utilize the virial theorem and make the calculation only once. All right, so this was problem 70. And the last one from this chapter is problem 99, which I really like because it makes some reference to the earlier chapters that you are actually responsible for the final. So we have a rubidium atom which has the mass 85 U, so 1 mole of this weighs 85 grams or so. Is at rest with 1 electron in an excited energy level. Okay, when the electron jumps to the ground state, the atom emits a photon of wavelength lambda equals 780 nanometers. Determine the resulting non-relativistic recoil speed V of the atom, and the recoil speed sets the lower limit on the temperature to which an ideal gas of rubidium atoms can be cooled in a laser-based atom trap. Using the kinetic theory of gases, estimate this lowest achievable temperature. Okay, so that's a mouthful and kind of looks scary at the first sight, but so when I first saw this, I wanted to ask this question. I wanted to have this suggested problem, but then I thought maybe it's too difficult. But when I tried to actually solve it, I saw that it is actually not that much difficult. So let's see if you agree with me when we look at this problem. So yeah, so we have this is problem 99. Let's see. We have a rubidium atom, so the M is 85 U, right? So there's some electron, it goes down to a lower level, and it emits a photon of wavelength 780 nanometers. Is that right? Yeah. And so this photon is, of course, it's carrying away some momentum, and this is going to lead to a recoil. right? So whatever momentum this photon is carrying, the atom is going to gain equal and opposite momentum in the other direction. So that is going to be given by the non-relativistic expression. M times V is going to be equal to h over lambda. Right? And you just need to substitute the values and get some answer. And if you want to use the tricks that I mentioned in the previous videos, what you can do is that is V over C equals HC over MC square lambda. Right, so this becomes 1240 electron volt nanometers. This is well, this 85 times about 2000 times half MeV, and then this is already given in nanometers, so you can carry out the cancellation easily and calculate V by C. And you are going to find that it's a small number. The result is actually non-relativistic. So did I calculate this? Yeah. So I looked it up. Probably I have no calculation here, but this comes to 6 times 10 to minus 3 meters per second. So this is very strange, right? So you're doing this weird quantum mechanical experiment, and you get something that looks like it's mismeasurable, right? You could imagine yourself moving at this pace. It's very small, like it's probably you probably cannot move at this pace, but on the average, maybe this is the pace that you're moving when you're sleeping or something, right? So this is something that what you would call macroscopic, even though everything here is certainly nanoscale, at atomic scale. Okay, but this is the velocity that you get for the recoil. This is just conservation of momentum. Now, this recoil speed sets the lower limit on the temperature to which an ideal gas of rubidium atoms can be cooled in a laser-based atom trap. So the idea here, this was part A. The idea here is that you have this atoms, you want to keep them there because you want to make some experiments on them, and you want them to interact in a certain way, and you also want to keep their temperature very low. So you do this by letting the system a little bit evaporate and just keep the coolest ones down there, and you do this by shining laser light on it, right, from every direction. So that creates a trap. Whenever the atoms try to move away, some laser light shifts them back. Yeah. They just stay in this prescribed region. Now, there is a price you're paying for this, though, because you're keeping these atoms there with the laser light. It leads to some excitation, right? And it could also be because of the interaction between the atoms. I'm not sure why this happens, but yeah, it leads to some excitation in the atoms, and this excitation, as a result of excitation, some photons are emitted, and those photons lead to this recoil. So even though you're trying to keep these atoms from moving, they will always have this photons being emitted, and they will always have some velocity, right? And the question is, what's the associated and temperature associated with this motion, right? And for this, we are going to use the kinetic theory that we have established. So here, because this temperature is very, very low, we only have the the motion of the translational degrees of freedom. I don't know what rubidium atom looks like, but since they are single atoms, in any case, the other degrees of motion will not come into play. So for that case, for translational motion, we will have 3½ kT is going to be equal to ½ v squared, right? Or ½ kT equals ½ Vx squared, if you will. So if you want to look at just one dimension, that's how we would write it. So these twos cancel, and then we can write our T as mv squared by 3k, right? And if you go ahead and calculate this, you find that this corresponds to 1.2 times 10 to minus 7 degree Kelvin, a very, very low temperature, right? So this is how you obtain such ultra cold atom traps, and this is not very surprising, right? The velocity we get here, even though it is sort of macroscopic, is much smaller, much smaller than the velocity of the air molecules, which we had seen at the beginning of the semester as to be of order of the speed of sound, hundreds of meters per second. And since the relationship between the temperature and velocity is not linear, temperature is proportional to square of the velocity. If you reduce the velocity by this 4 or 5 orders of magnitude, then your temperature is going to drop by a 10 orders of magnitude, and this is indeed that much less than the room temperature, which is just hundreds of Kelvin, right? 300 Kelvin or so. Okay, so this number does make sense. You would expect for these speeds of atoms, the associated temperature will be very low. Whether it makes sense to talk about the temperature of these atoms is, of course, another question, which I'm not going to try to answer. Okay, thank you very much.